Hi, in today's class we're going to connect the D function to the Bohr model. And shown here then are the D functions of the 3p and 3s AOs, and they both have the same principal quantum number n equals 3. And in the Bohr model we know that the total energy is proportional to z squared over n squared. 3p and 3s are orbitals on the same atom. The z is the same. The n is the same as the 3. They should have the same total energy. We saw that when we drew the Bohr energy diagram. There's the E equals 0. Here is the n equals 1, which we now know is the 1s. Above that is the n equals 2, which we now know is 2s and 2p with the same principal quantum number 2. And above that is the n equals 3, which is 3s, 3p, and 3d. So the Bohr model tells us that 3p and 3s should have the same energy, and we'll be able to see why this makes sense looking at the D function. So the 3p and 3s have little bumps and the big bump. The electron is spending its time mostly in the big bump. And you can see that they look like waves. For 3p, the wavelength is proportional to that distance, and in 3s, the wavelength is proportional to that distance. And those wavelengths then are very much the same. So lambda 3p is around the same as lambda 3s. By the de Broglie relationship, we know that p is inversely proportional to 1 over lambda. And therefore, since the lambdas are the same, the momentum of the 3p and the momentum of the 3s should also be the same. Kinetic energy is proportional to velocity squared, and velocity squared is proportional to momentum squared. Ek of 3p then should be around the same as Ek of 3s. And finally, Ek, we know by the virial theorem, is proportional to Et. And so the Et of 3p, based on the D functions, should be around the same as Et for 3s. And that's what the Bohr model tells us. And while we're looking at Ek and Et, why don't we also look at Ep? Et is proportional to Ep. So now we know the potential energy of 3p is going to be around the same as the potential energy of 3s. Potential energy is proportional to z over r. And for the same atom, z will be the same number of protons. And therefore, we know that r of 3p and r of 3s are around the same. And we can see that in the graph. R is the average size. And we have for the 3p that the average position is around here. If we look at the two bumps, and for 3s, the average position is roughly the same. So again, the D function is telling us that the size of the 3p and the 3s are the same, again in accordance with the Bohr model. And we can look at let's look at 3D now. So here's 3D, and what should we do with 3D? Let's just start with the R's. So the R for 3D is around here, the average R, and if we look at the two bumps of the 3p, it's around the same value. And so we see that R of 3D is around the same as R of 3p. Potential energy is proportional to z over r, and therefore we expect the potential energies of 3D and 3p to be the same. potential energy is proportional to total energy. So the total energy, as predicted by the Bohr model, here, the total energy of 3D is the same as the total energy of 3p. And now, for good measure, let's look at EK. E total is proportional to EK. EK of 3D, therefore, should be the same as EK of 3p. EK is proportional to p squared. So P of 3D should be around the same as P, the momentum of 3p. By the de Broglie relation, P is proportional to 1 over lambda. Lambda of 3D should be around the same as lambda of 3p. And again, we see that's true. The electrons are spending most of the time in the big bump. For the 3D, it's going to be proportional to that length, the wavelength, and you can see that for 3p, it's the same length. And so the D functions bear out the same story that we understand from the Bohr model. And we'll continue with this next in class tomorrow.